So today what we're going to be looking at is we're going to be looking a little bit more at reactions, and in particular, we're going to talk a little bit about the energy of reactions. So thinking about some of the ideas of what drives a reaction. Um, why does a reaction take place? Why are some reactions endothermic or exothermic? And where does this idea of chemical potential energy come into play? So first, let's go ahead and talk about the energy of reactions. We want to remember something that we have talked about before, and that is the chemical potential energy. And the chemical potential energy is the energy that is stored in the chemical bonds of a substance. So that force that holds them together stores energy. The amount of energy that's stored between two atoms or in that bond depends on two different things. It first depends on the kind of atom. The amount of energy stored between two carbon atoms or a carbon and a nitrogen atom are going to be different. So we need to be looking at the kinds of atoms that are being bonded together. And the second thing is the arrangement of atoms. We're going to be looking at some of the things like, is it a double bond? Is it a single bond? So don't worry too much about this because a lot of times there's just going to be a table that tells you. But it is important to know that there are two different things that are kind of coming into play when we think about the energy of reactions or the chemical potential energy. During a chemical reaction, and you guys have kind of been looking at this, you guys looked at this idea of balancing chemical reactants, and we looked at this idea that when a reaction occurs, we have a substance and it's changing into a new substance. So in order for that to happen, we are taking those bonds and we are breaking them, and then we're reforming them in different ways. And when we reform them in different ways, we're creating these new substances. When we break bonds, that requires energy. So energy has to be put in. I like to think of this idea as if like you have um, let's say a pencil and you want to break it into two pieces. Think of that pencil as a bond. If you want to break that pencil, you have to input energy. Energy has to go into it. And you're going to kind of input that energy when you hold the two ends and you kind of try to push them upwards. So breaking bonds requires energy. And remember, when something absorbs energy or requires energy, it's called an endothermic process. So the opposite of that is forming bonds. Forming bonds actually releases energy. And one of the reasons why this releases energy is that when we think of atoms, they form bonds to become more stable. And when something becomes more stable, that means that it's lowered energy. So to go from something like these individual atoms to a bond, you're going from something that's high energy to low energy. So forming bonds releases energy, and that means that that process is exothermic. So breaking bonds requires energy, forming bonds releases energy. So here we have an example. We have the example of hydrogen reacting with iodine and is producing hydroiodic acid. So when we think about this, we have some hydrogen, um, a hydrogen atom, so H2, it's a diatomic, which means that it always comes in a pair. And there's that bond right there that's holding those atoms together. Now we're going to break this bond, and what's going to happen is that it's going to release energy, and it actually releases 436 kilojoules per mole. So that's going to release, that's actually not going to release, excuse me, I misspoke. It requires that much energy. So that much energy needs to be supplied in order to break that. And then here we have iodine. So in order to break that bond, we have to input 151 kilojoules of energy. So in total, in order to break those two bonds, we have to input 587 kilojoules of energy per mole. Now, when we form our substance, we're going to be releasing energy. So the amount of energy that's released when that bond forms, hydroiodic acid or HI, what we see is that in order to form that bond, it's going to release 297 kilojoules per mole. And since we have two of them, it's going to do double that. So the total amount of energy that's released when bonds formed is 594 kilojoules per mole. One thing that I want to pay attention, that I want you to pay attention to is this idea is that notice that the amount of energy required is not necessarily equal to the amount of energy that's released. So what happens to that extra energy that's released? We have this idea of the law of conservation of energy. So the law of conservation of energy, we've looked at this law before. In any chemical reaction, energy is neither created nor destroyed. If more energy is required to break the bonds than is released in the formation of the new bonds, so you have to input more energy, you don't get that much energy back, the overall amount of energy or the difference between those, that energy has to be absorbed from the surroundings. So it's actually going to be taking energy from the surroundings. It's going to steal that energy from air molecules or from heat from the surroundings. So it's going to be absorbing that energy, or it's going to steal that energy from the surroundings. On the other hand, like the example that we just looked at, if more energy is released from forming new bonds than is required to break the bonds, then energy is released to the surroundings. So very quickly, let me go back. So here we have, there is 587 kilojoules per mole that is required, but it's going to release 594 kilojoules per mole. So the difference between these two values, more energy is released. Well, how much energy is actually going to be released? Well, if we subtract these two values, what we'll see is 7 kilojoules of heat are going to be released from this reaction. So notice that the energy is going to be released. If this was opposite, if we had more energy that is required to break the bonds, what we see is that energy would then be absorbed. We're going to look at an example of this in just a minute. And we're going to be using this bond table right here. So what we have right here is the average bond energy. So this is where I was saying that you don't need to know these bond energies. Usually you have a table like this in front of you that will help you do some calculations. So what we're going to do is we're going to work on this example. We want to use the table of average bond energies, and we want to estimate the energy needed to break bonds of the reactants and the energy released from the products forming when N2 plus O2, or nitrogen plus oxygen, forms 2 moles of nitrogen monoxide. One of the things that's important that they actually note here is that N2 is a triple bond. O2 and NO have double bonds. And that's really important because notice that the bonds, how many bonds they have does change the energies. So let's go ahead and solve this problem. All right. So let's look at our reactants. So our reactants is N2 plus O2, or nitrogen and oxygen. So what we have is we have nitrogen, which we were told was a triple bond, so there it is, and oxygen, which is a double bond, and it's right there. So what we're going to do when we look at this is notice that there's no coefficient in front, there's no number in front, so it's just one of each. So what we're going to say is that the energy required, so we'll say reactants, let me write this out, reactants, it's a little messy, is going to be 945, and this is kilojoules per mole, plus 498 kilojoules per mole. All right, so let's go ahead and add that together. This is going to be the energy that's required. So 945 plus 498. So the energy required is 1,443 kilojoules per mole. So this is required to break bonds. Okay, let's look at NO. Notice that we have 2 of them. So when we look at this NO, we need to show that there is going to be 2 of them, because we don't have just 1 molecule of nitrogen monoxide, we have 2. So our products, we're going to have 607 kilojoules per mole plus 607 kilojoules per mole. And what we see is that the amount of energy that's released is going to be 1,214 kilojoules per mole. So this is going to be released. So notice this one. The amount of energy that is released is less than the amount of energy that is required. So it's going to absorb a certain amount of energy from the surroundings, and the amount of energy that it's going to absorb from the surroundings. So let me write this down. We're going to say reactants is greater than products. And so what we see is that if we subtract those two values, 1,443 minus 1,214, it's going to absorb 229 kilojoules per mole from the surroundings. So that's going to have to come from somewhere else. Where on the other example that we saw, it was going to release that amount of energy. Let's go ahead and move on. So when we think about this, we can label those two types of reactants as endothermic or exothermic. So this is the first reaction that we looked at. So notice that we have our hydrogen and our iodine, and then we have our 2 moles of hydroiodic acid. So remember, we said that because the amount of energy released is more than the amount of energy that's absorbed, some energy is going to be released. This is called our net energy released. And because we have more energy being released, this means that this reaction is overall exothermic, because overall, when this reaction's done, it's going to release energy. So here's our chemical potential energy. We can kind of map this. We go from 787 kilojoules per mole to 594 kilojoules per mole. It's going to release that much amount of energy. On the other hand, when we look over here, this is the one that we just solved. We had our reactants, which require 1,443 kilojoules of mole, or excuse me, kilojoules of heat per mole, but we only released this much. So remember, we said if we subtract those two values, the amount of energy that needs to be absorbed is a positive 229 kilojoules per mole. So an overall, more energy needs to be absorbed in order for this reaction to take place, and this is what we call an endothermic reaction. So here's what our overall idea is. If the products release more energy than the reactants absorb, then the reaction is exothermic. If the products release less energy than the reactants absorb, then it's an endothermic reaction. And it all depends on those bond energies. The last idea that we're going to be looking at is collision theory. Collision theory allows us to kind of think about, why does a reaction take place? What needs to happen in order for our reactants to turn into products? So the main idea is that when we have a chemical reaction, the bonds of the reactants are only broken if the molecules collide with enough energy. If they don't collide with enough energy, they're just going to bounce off of each other. So those molecules need to come in contact, and they need to collide with enough energy to form the new products. Well, how quickly that happens is called the rate of the reaction. Now, some reactions can take a long time, and some reactions can happen pretty quickly. So for example, if you were to light a match, that's a pretty quick reaction. That happens, if in our eyes, almost instantaneously. So I said, think combustion. However, some reactions can definitely take a little bit longer and are a little bit slower. So I like to think of this idea as like something that's rusting. If you leave something out, rust takes time to form. It is a slower reaction. It doesn't happen that quickly. So collision theory states that molecules must collide with enough energy to break those bonds. And then the rate of the reaction is how quickly does the reaction occur. Now, One way that we could actually manipulate the rate of the reaction is by changing the temperature. So here we have the reaction rate and the temperature. The number and the energy of the collisions between molecules in the container determines the reaction rate. So again, if we have collisions, molecules colliding with more energy, we are going to be able to produce products more quickly. If we have more reactants, well, more collisions are going to occur, and hopefully more of those collisions are going to be successful so that more products um, can be created. So when we increase the temperature, remember what is happening is that we are increasing how quickly those molecules are moving around. If they are moving around faster, they're going to be able to A, collide with more energy, but also we're going to have more collisions in general because they're moving around faster. So they're going to be able to bump into each other more frequently. So with those two ideas, we are actually increasing the rate of the reaction. So what we looked at today is we looked at this idea of the energy of a reaction. We were able to actually calculate the energy of a reaction that's released or absorbed based off those bond energies. We also looked at this idea of collision theory and rate of reaction. So what you're going to be doing now is you're going to be using our program on Savvis, and you're going to be taking a quick little practice quiz. This quiz will not be something that's graded. I want you to take the quiz as a practice to see how well you kind of understand these ideas.